Have you ever felt like humanity is just desperately trying to cure the planet's climate illness without, actually taking the time to read the patient's medical chart?
Oh, absolutely. Like we're just guessing in the dark.
Right. Welcome to this deep dive. Today, we're asking a pretty massive question for y'all. What if we've been treating the Earth like a passive victim when it's really an active patient that has already diagnosed itself?
Yeah, because we see the symptoms, right? The rising temperatures, the dying forests, extreme weather.
And we just start throwing generic bandages at the problem. I mean, we
Yes.
haven't even taken a pulse.
It's literally the ultimate form of planetary medical malpractice.
Yeah.
I mean, we prescribe all these treatments based on, like, surface level satellite images.
Or just basic atmospheric thermometers.
Exactly, completely ignoring the fact that the Earth has this massive, highly detailed biochemical memory of its own health.
Yeah.
I mean, the planet has survived massive extinction events. It's balanced unimaginably complex climate systems for
Yeah.
eons. It knows how to heal.
The barrier has just always been language, right?
Yes, exactly.
The chart is written in the dirt, and we just haven't had the translator. So today, our mission is to unpack a truly revolutionary document that provides that exact translation.
And it is a fascinating document.
It really is. We are looking at a 2026 doctoral thesis from Nova Amazonia by Costa Rican researcher Martin Gutierrez Guerrero. And the title alone is a lot to chew on.
It's a bit of a mouthful.
It is. It's called Nanotechnology and Advanced Materials, Science Applied to Quantum Computing. We are going through detailed academic notes, peer-reviewed summaries, and transcripts surrounding this landmark document.
There's a lot of material there.
So, okay, let's unpack this. The thesis proposes this mind-bending intersection of quantum physics, living bacteria, and of all things, leftover coffee waste.
Which sounds insane at first.
Totally insane. But our goal for you today is to explore how this technology acts as the ultimate, planetary stethoscope, while also thoroughly debunking some incredibly popular sci-fi myths about how nature actually works.
Yeah, to really grasp why this specific technology was engineered in the first place, we have to start with a fundamental philosophical shift that Gutierrez Guerrero outlines.
Okay, lay it on.
Well, historically, humanity has acted as a deaf observer. We walk into the forest, decide what's broken based on our own limited metrics, and then we just impose artificial fixes.
Right, like building a concrete dam.
Or planting a million trees of a single non-native species. We don't actually ask the soil what it needs.
It's like a terrible doctor who walks into your hospital room, completely ignores your symptoms, hands you a random pill, and just walks out.
That is the perfect way to look at it.
Yeah.
Gutierrez Guerrero realized that to get the right treatment, you need a high-dimensional medical diagnostic interface.
A stethoscope.
Exactly. That is what he built. He calls it an Intelligent Autonomous Bioquantum System.
Or SBAI for short.
Right, SBAI. And it is not just another environmental sensor that measures moisture or temperature. It's an actual biological communications bridge.
Engineered specifically to talk to the planet on its own terms.
Yeah.
So if SBAI is the stethoscope, what exactly are we listening for when we, plug this thing into the dirt?
We are listening for biological prescriptions. The system looks for data on stress, resilience, and recovery.
Written directly into the soil chemistry.
Yes, the soil chemistry, the fungi, and the water layers. But to extract that data, the thesis transitions from this really elegant philosophy into some incredibly hard engineering.
Yeah, the math gets intense.
Very intense. It relies on a central taxonomy called ICBM, which stands for Multi-Scale Bioquantum Conductance Interfaces.
Multi-scale bioquantum conductance interfaces. Okay, we need to break that down for everyone listening because the multi-scale part is really the blueprint here.
Right, it's divided into 3 levels.
Exactly, 3 exact operational levels. Let's start with the very, very small, the micro scale.
This is where we hit the quantum level. Gutierrez Guerrero engineered this hybrid control loop where information, in the form of electrical signals, is transferred out of living biology.
And into human hardware.
Using quantum tunneling.
I want to make sure we visualize this properly. Quantum tunneling is that phenomenon where a particle, like an electron, passes through a physical barrier that it mathematically shouldn't have the energy to cross.
Right, classical physics says it bounces off.
But in quantum mechanics, it essentially ghosts through a solid wall.
A very tiny wall, specifically a 1.5 nanometer gap in this system. On one side of that gap, you have living bacterial cytochromes.
Cytochromes.
Yeah, these are naturally occurring proteins inside electrogenic soil bacteria. They act as microscopic wire terminals, transferring electrons as the bacteria metabolize.
And on the other side of that 1.5 nanometer void.
You have a biogenic acceptor. It's basically the landing pad for the electron.
And this is where the coffee waste comes into play, which I have to admit, it sounds like a complete gimmick at first. Why coffee?
I know, right? But it's actually a masterclass in material science. The acceptor needs to be highly conductive, but traditional graphene is incredibly expensive.
And toxic to produce.
Exactly. So the researcher found that if you process biogenic waste, specifically leftover coffee grounds, you can create a cheap, highly effective form of carbon graphene.
But because it comes from biological waste, its physical structure isn't like a perfect uniform grid, right?
No, it's messy. Very messy.
So how do you predict the movement of an electron jumping out of a living bacterium into a messy piece of coffee carbon? That sounds impossible.
Well, you use two specific mathematical frameworks. First, the WKB approximation.
Okay.
Without getting bogged down in the formulas, WKB calculates the exact probability wave of that electron successfully ghosting through the 1.5 nanometer gap.
Right.
Once it lands on the coffee graphene, you use something called the Anderson-Hamiltonian.
The Anderson-Hamiltonian.
Yeah, think of the coffee graphene's atomic structure like a chaotic, incredibly crowded subway station during rush hour.
Oh, that's a great analogy.
The Anderson-Hamiltonian calculates how the electron navigates that disordered chaos without getting trapped or localized in a dead end.
That is wild.
Yeah.
I mean, we are using advanced quantum probability math to map the exact route of an electrical signal as it jumps from a living bug into a recycled coffee bean.
It's unbelievable engineering.
It really is. That's the microscale. But a single electron jumping across a gap doesn't give us a medical chart of the Earth.
No, not at all.
We have to zoom out to the mesoscale.
The mesoscale is the network level. Here we move from single electrons to vast colonies of living bacteria.
Which are physically tangled up with fungal hyphae.
Right. If you dig into the soil, hyphae are the microscopic root-like threads of fungi. The thesis introduces physical hardware units called bio-3D phytocells that integrate with this tangle.
I want to paint a picture for the listener here. Don't think of this like a traditional silicon computer chip with rigid gold wires.
No, it's alive.
Think of the mesoscale as a living fiber optic network beneath your boots. The fungal threads act as the physical cables spanning the forest floor.
And the bacteria act as the microscopic data routers. They're constantly adapting to the chemical traffic in the soil.
That is exactly how the software visualizes it, right?
Yes. To process the data moving through this living fiber optic network, the system uses graph neural networks, or GNNs.
Which are great for irregular mapping.
Exactly. A GNN is an AI architecture that excels at mapping complex, irregular relationships, which perfectly describes a chaotic biological ecosystem.
So the AI treats the bacteria and fungi as dynamic, constantly shifting nodes in a circuit.
Spot on, and managing that entire circuit is another layer of AI, a soft actor critic, or SAC, reinforcement learning algorithm.
Okay, let's slow down on the SAC algorithm because this brings up something that genuinely stopped me in my tracks while reading the sources.
The viability rule.
Yes, the AI has a strict, mathematically non-negotiable rule hard-coded into its behavior.
Yeah.
It must maintain 95% cell viability in the bacteria at all times.
It is the defining constraint of the entire project.
Which is crazy to think about.
Well, in reinforcement learning, an AI tries to maximize its reward points. Gutierrez-Guerrero engineered the reward function so that biological survival is paramount.
Wait, I have to challenge the practicality of this. Just, play devil's advocate for a second.
Sure, correct.
Imagine a scenario where a mining facility just dumped a massive amount of toxic heavy metals into a river ecosystem.
A critical emergency.
Right. We need that pollution data instantly to warn downstream communities and shut down the water supply.
Yeah.
Are you telling me that this AI will intentionally throttle the data transmission just so some soil bacteria don't get overly stressed out?
Yes, absolutely.
How does an algorithm prioritizing biological rest help us stop an ecological disaster?
Because if you burn out the bacteria to get the data 5 seconds faster, your sensor permanently dies.
Oh.
Yeah, this isn't a piece of silicon you can just swap out. The bacteria are the hardware.
Right. I wasn't thinking about it like that.
The AI understands that extracting data requires the bacteria to ramp up their metabolic rate. If the AI pushes them too hard, they accumulate oxidative stress and die.
Causing the whole network to collapse.
Exactly. The SAC algorithm calculates the absolute maximum data extraction rate that still allows the bacterial colony to regenerate. It sacrifices a tiny bit of immediate speed for permanent, self-sustaining longevity.
An AI that forces itself to be gentle. The thesis calls this an empathetic interface, doesn't it?
It does. The survival of the biological substrate is completely inseparable from the data it produces.
It shifts our relationship with technology from extraction to symbiosis.
Beautifully said.
Mm-hmm.
And that symbiotic network scales up to the final tier, the macro scale.
The planetary level.
Right. The Bio3D phytocells hook into the global mycorrhizal network, what ecologists often call the Wood Wide Web.
To read the entire forest as a monumental analog biocomputer.
Exactly.
And here's where it gets really interesting, because the moment you introduce the concept of the Wood Wide Web, and we've just spent the last 10 minutes discussing quantum tunneling, it is incredibly easy for the imagination to run wild.
Oh, absolutely.
Think about the last time you watched a sci-fi movie where an alien forest was this glowing, interconnected, magical brain that communicated instantly across the planet.
It is a very seductive idea. The concept of a quantum planet memory floating around in the mycelium has become wildly popular in pop science over the last decade.
But Gutierrez Guerrero's thesis performs a necessary, almost brutal act of scientific responsibility here.
It really does. It quantitatively refutes the quantum myth.
Brutal in what way? Let's give the listener the math here.
Well, the thesis uses the hard physics of thermal decoherence to prove that a quantum mycelial network is thermodynamically impossible.
Because quantum states are so fragile.
Incredibly fragile. Quantum states like entanglement or superposition fall apart instantly. In human-made quantum computers, we have to keep the processors at near absolute zero.
Colder than deep space.
And isolate them from all stray electromagnetic fields just to keep the quantum state stable for a few milliseconds.
And a forest floor is the exact opposite of an isolated vacuum. I mean, if you dig your hands into the dirt, it is damp, it is warm, it is full of friction.
Chemical reactions, vibrating molecules. It's pure chaos. In that humid, room temperature biological environment, any delicate quantum state in the soil would collapse into classical physics in a fraction of a nanosecond.
Oh.
The math in the thesis demonstrates that the gap between the sci-fi myth of a quantum forest and actual physical reality is a staggering 18 to 25 orders of magnitude.
18 to 25 orders of magnitude. To put that in perspective for you listening, that is not a rounding error.
Not all.
That is like confusing the size of a grain of sand with the size of the observable universe. It mathematically obliterates the concept.
Completely. There is no known biological insulation that could preserve quantum coherence across a damp forest floor.
None whatsoever. So quantum tunneling we discussed earlier only happens across that 1.5 nanometer microscopic gap.
Yes. Once you zoom out to the forest, the physics change entirely.
Which raises an uncomfortable question. If the math is off by 25 orders of magnitude, why did the romantic idea of a glowing, quantum-entangled forest become so deeply ingrained in our culture?
It's a great question.
Do we just prefer the illusion of magic over the reality of biology?
I think humans are just drawn to narratives that make the natural world feel mystical. We think that if the forest is quantum, it's somehow more profound or worthy of saving.
Right.
But the irony is that refuting the quantum myth doesn't kill the wonder of the planet. Grounding it in hard science reveals a reality that is far more impressive.
The planet's memory is real.
It is real. It's just not quantum. It is purely classical.
So let's explore that classical memory. What does a non-quantum physical memory actually look like in the dirt?
It looks like stable carbon and nitrogen isotope stratification.
Okay.
It looks like epigenetic DNA methylation. And it looks like heavy metal bioaccumulation.
Let's break those down, starting with epigenetic DNA methylation. How does DNA act as a historical memory bank?
When a forest experiences a severe trauma, say a 10-year drought, the plants and fungi don't just endure it. They chemically alter how their genes are expressed to survive.
Just to get through the stress.
Right. And they often do this by attaching a tiny molecule called a methyl group to specific parts of their DNA. It turns certain survival genes on or off.
Okay, I follow.
But the key is, even after the drought ends, those methyl groups remain. It's like dog-earing a page in a biological history book.
That's fascinating.
Decades later, SBAI can read that dog-eared page and know exactly what climate traumas that ecosystem survived.
It's literally a physical scar of history left in the molecular structure of the ecosystem.
Yes, and SBAI is the high-dimensional reader translating these classical scars.
But processing that sheer volume of historical and chemical data has to require immense computational power.
It does. The system utilizes transformers with attention mechanisms.
Like the language models.
Exactly. If you're familiar with how advanced language models can predict the next word in a sentence by paying attention to the context of the whole paragraph, This AI does the same thing with chemistry.
So it reads the soil.
It reads the classical isotopic data of the soil, pays attention to anomalies, and can predict the spread of a toxic industrial spill in milliseconds.
Okay, so we have firmly grounded this technology in reality.
We have.
We've gone from quantum tunneling in a 1.5 nanometer gap through an empathetic AI managing fungal networks, all the way up to reading the classical epigenetic memory of the forest.
It's a journey.
It is. Now let's bring this out of the theoretical lab and into the real world. Why does this matter for the actual people living on the front lines of these ecosystems?
This brings us to the socio-economic endgame of Gutierrez Guerrero's thesis, which is fundamentally about environmental justice for the global south.
Because we have to remember the hardware here. These Bio3D phytocell sensors are decentralized,
And they are printed using local biogenic coffee waste.
which drops the production cost down to mere pennies per kilogram.
Exactly. And this completely changes the power dynamic of environmental defense.
How so?
Think about the historical precedent. If a local community in Nova Amazonia or Costa Rica suspected that a multinational mining conglomerate was leaking poison into their groundwater, they were largely helpless.
They couldn't prove it.
Right. They had to rely on expensive imported technology, wait for foreign environmental agencies to validate their claims.
And fight billion-dollar corporate lawyers in the meantime.
It was an insurmountable asymmetry of power. The community lived with the poison while waiting years for the bureaucracy to catch up.
But by making the hardware virtually free and the AI software autonomous, local communities achieve actual technological sovereignty.
They can physically deploy these biometric sensors themselves.
So they have a mathematically unassailable, real-time diagnostic tool to audit illegal mining pollution.
Yes, and the thesis highlights auditing for incredibly dangerous pollutants, things like uranol and hexavalent chromium.
But the technology goes a step further.
Oh, it goes much further.
Because it's an empathetic interface tied into living biology, it doesn't just passively beep when it detects heavy metals. The bacteria can actively bioremediate the water.
This is the true genius of integrating living hardware.
I have to pause you there, because to a layman, bioremediation sounds like magic. How does a microscopic organism clean up hexavalent chromium?
It's wild biology.
Right. I mean, they don't have little microscopic hazmat suits. How do they survive eating toxic heavy metals?
Well, they don't eat it in the human sense. They alter its chemical state through a process called enzymatic reduction.
Okay, break that down for us.
Hexavalent chromium is highly soluble in water, meaning it spreads easily and is highly toxic to living tissue. But certain electrogenic bacteria in the SBAI network possess specific enzymes.
And when they bump into the chromium?
When they encounter the hexavalent chromium, they transfer electrons to it, chemically reducing it to trivalent chromium.
Then what's the difference?
Trivalent chromium is mostly insoluble. It turns into a solid precipitate and drops out of the water column, rendering it relatively harmless.
They literally force the poison to solidify, so it stops poisoning the water.
Yes.
And the AI is managing this entire process, ensuring the bacterial colony doesn't overexert itself while cleaning up the spill.
It's all connected.
It completely flips the entire script of environmentalism. Think about it. It's no longer about passive conservation. It's no longer about waiting for a disaster, begging a court for an injunction, and trying to clean up a dead river 10 years later.
No, it is active, intelligent co-collaboration with the environment.
The power to diagnose the illness and trigger the Earth's natural immune response is placed directly into the hands of the people who live on the land.
It severs the reliance on Silicon Valley or external tech conglomerates.
So what does this all mean? We've journeyed from the subatomic physics of quantum tunneling and leftover coffee grounds, dismantled our sci-fi fantasies about magical glowing forests, and arrived at the democratization of global environmental defense.
It means that true environmental emancipation, as the thesis notes, comes from mastering hard, irrefutable reality.
We don't need magic.
We don't need to invent extraordinary myths about nature to save it. The actual physics and the real biology are powerful enough, provided we build the tools to understand them.
There are some incredible philosophical peaks in this text. The Costa Rican researcher outlines a core philosophy that I think perfectly summarizes the shift in perspective we need.
Oh, I know the quote you're talking about.
Yeah, he says, the goal of this technology is to forge the sciences of the future with our hands in the dirt, but our eyes aimed at the stars.
It's a striking reconciliation between high-tech ambition and ancestral territory. It proves that advanced science doesn't have to alienate us from the natural world.
It can be the exact mechanism that integrates us back into it.
Exactly.
And there's one final thought from the thesis that serves as the ultimate closing manifesto for this deep dive. Gutierrez Guerrero writes that the true quantum leap of informatics isn't about creating an artificial mind that replaces us.
It is about transforming ourselves into the conscious, listening link of a biosphere that has been waiting for eons to be heard.
We finally built the stethoscope.
Now it's just a matter of having the courage to listen to the diagnosis.
Which leaves you with one final provocative thought to mull over. If this incredibly low-cost technology successfully turns the Earth's biosphere into a readable, real-time diagnostic dashboard, what happens to global politics when the planet itself becomes an irrefutable scientific witness in a court of law against those who pollute it? Could the medical chart of the Earth literally be called to the stand to testify against us?